So you can start now, sir. Thank you, sir.
Okay, thank you. Okay, I think we need to start all over since we were not streaming online. We were not streaming on YouTube when I started originally. So I think we need to start all over again. Now, my name is Taufik Ogumbayo. I'll be taking you a topic in Fsc112. Of course, Fsc112 is Introductory Chemistry, and that topic is chemical kinetics. Now, before we even talk about the introduction, because the first thing you want to know is what is even chemical kinetics, what does it deal with? Now, the number one thing is that we know that chemical reactions, or even if you didn't know now, I think you should know now that chemical reactions actually occur at different rates. Some reactions occur very fast, while some occur very slow. In fact, some reactions actually occur at a rate that you hardly notice that the reaction is going on. Take, for example, the reaction between iron and water that we call rust. Immediately iron get in contact with water, you won't notice anything that the reaction is going on. You won't see anything. In fact, it takes a while before you begin to even notice it. When I say it takes a while, sometimes it takes days for you to begin to notice that anything is even going on between iron and water. That is a reaction that is actually occurring very slow. But of course, that is even a little fast. There are some reactions that are even much slower than that. And another example is if you throw, say, for example, a piece of sodium metal, if you throw it into water, you will quickly notice a violent reaction between that piece of sodium and water. That is a reaction proceeding at very slow, at a very fast rate. Now, that is contrasting two types of reactions, one that is very slow, one that is very fast. And that is telling you that when you're talking about chemical reactions, rates are very different for different type of reaction. Now, and this is what chemical kinetics deals with. This is a study of the speed or rate of chemical reaction. That is, chemical kinetics study the rate at which chemical reactions happen, but that is not all. It also studies the mechanism of that particular reaction. If you have a reaction taking place, a reaction between, for example, A and B, sometimes we'll get to write or we'll get to explain this better, that what pathway did the reaction take? So when you're talking about kinetics, you're talking about the rate of reaction and the pathways through which this reaction took place. That is what chemical kinetics is all about. Rate of reaction, mechanism of reaction. Rate of reaction, the pathway through which the reaction took place. That is what we study under this branch of chemistry called chemical kinetics. Now, in this course or under this topic, you will learn how to determine rate of reactions. That is, anytime you have a reaction, you'll be given the data and you can determine the rate at which that reaction took place. Then the second thing is, how do we express this rate mathematically? It's not just all about the rate of reaction. There's an expression. There's a way you try to express the rate at which this reaction takes place. You should also be able to write this rate at the end of this topic. Now, at the end of this topic also, we should also be able to determine, because at the end, when we talk about rates or the rate at which a reaction happens, there are also factors that contribute or that affect the rate at which this reaction takes place. And those factors are factors like pressure, temperature, concentration, and catalyst. How do they affect the rate of reaction? These are the kind of questions you should be able to answer at the end of this topic. Now, like I said earlier, we want to deal with those factors that affect the rate first. So, and as I said earlier, there are those factors that affect the rate. The number one factor is actually the nature of the reacting species itself. If you go back to the original example I gave, where we were talking about iron and metal and sodium and metal. Iron and metal, iron and water, and sodium and water. Iron reaction with water, sodium reaction with water. One was fast, one was slow. There was actually a constant in the two. We had the water in both cases. But in the case of iron, it was slow. In the case of sodium, it was fast. That is telling you that the nature of the reacting species is important. The nature of iron is actually why the reaction was slow, why the peculiar nature of sodium is also why the reaction was actually very fast in the case of sodium and water. So the nature of the reactants are very important. The second part, or the second factor, is the temperature. The second factor is the temperature. Now, when you increase temperature, when you have an increase in temperature, the velocity of reaction increases. When you increase temperature, you remember that even in your O-level physics, one of those things that happens is that when you increase temperature, the species actually gain more kinetic energy. And when they gain more kinetic energy, of course, you expect them to move more violently with increase in temperature. And when this happens, of course, you are going to have more collisions because when the temperature increases and they gain more kinetic energy and their movement become faster, then that means collision also will become faster. Then, and of course, when collision becomes faster, the rate of reaction also becomes faster. And when the temperature decreases also, of course, you have the reverse taking place. Now, there are many gaseous reactions which take place very slowly at ordinary temperature that, of course, you are not, this is not, you don't need to do anything. At room temperature, there are certain reactions that can take place. And there are certain reactions that won't even take place at all at room temperature. You're going to have to raise the temperature for you to be able to have that reaction. Or even when I was talking about iron and water at ordinary temperature, there are certain factors that when you tweak those factors, and temperature is one of them, that rate can actually be increased. But the analogy I gave earlier was just at room temperature. That reaction was still taking place. But if you change the temperature of the environment, or you change the temperature of where you have the iron and the water, of course, the rate of reaction will also increase. But it has been found, it has been approximately found that for every 10-degree rise in temperature, the velocity of reaction gets doubled. That if you want to tweak the rate of reaction, this is how temperature affects, but we're going to talk more about this also. Now, also the second factor
We can no longer hear you, sir.
Okay. Sorry about that, guys. I wanted to see if I would be able to write or, but since that was impossible, in fact, maybe that actually led to the problem we had. So because I was just trying to like demonstrate to you the relationship between rate of reaction, because we're talking about concentration. And the thing with concentration is that when we say that when rate of reaction increases, when concentration increases, rate of reaction increases. It's the same thing as pressure. But when a reaction is taking
Increase your volume, sir. We can barely hear you.
Okay. Now go. Can you hear me now?
We can't hear you, sir.
You can't hear me.
No.
This is the highest volume because I switched from my.
Some of them can hear you. You can continue. Continue,
okay.
Sir.
Okay. All right. So
they can hear you.
Okay. Now, since the concentration of reacting species, they don't remain constant in the course of the reaction, because when we say that when concentration changes, that means rate of reaction will also change. So when you are in the middle of a reaction, or when immediately a reaction commences, you know that concentration will start decreasing. That means that the rate of reaction will not remain constant. For some reactions, the rate of reaction will change as the reaction progresses. And the reason is simply because the concentration of the reactants are also changing. It's not for all reactions. There's a reaction called zero order reaction. We'll get to that. But for majority of reactions, the rate will not remain constant throughout the reaction because the concentration is changing. Concentration of reactant decreases with time in the course of a reaction, and therefore rate of reaction will also decrease with time in the course of a reaction. Now, if you look at this, this is a demonstration, or this is a demonstration of the relationship between concentration and time in the course of a reaction. If you have a reaction A plus B to give you C. Now, if you look at what is going on here, if you look at reactant A, the concentration is decreasing. Reactant B also, the concentration is decreasing. But if you look at the product, the concentration of the product is increasing in the course of the reaction. Now, you can determine rate of reaction using any of these reactants. You can use A to determine rate of reaction. You can use B to determine rate of reaction. You can also use C to determine rate of reaction. If you want to determine the rate of reaction, you just need to monitor what happens to the concentration of one of the reactants in the course of the reaction. We can just monitor the concentration of this A over time and determine the rate. We'll learn how to do that. We can also just look at the concentration of reactant B, how it changes, and use that to determine the rate of reaction. Or we can also just look at the concentration of reactant C, product B, how it increases, and we can use that to determine the rate of reaction. Now, this is the relationship between rate and concentration. As concentration increases, rate of reaction increases. And as concentration decreases, rate of reaction decreases. I was going to draw, but I don't want to do that again so that I don't get ripped off again. But this is actually the reverse of what happens in here. Because if you look at the curve we have here, this is talking about increase in concentration. But in the course of a reaction, what you're going to have is going to be a decrease in concentration, so that the curve is going to be the other way around. Instead of the curve moving from your moving down from your moving from your lower left to upper right, what you're going to have is going to be from upper left to lower right for when a reaction is actually going on. But I just don't want a mix-up. That's why it's just all about telling you the relationship between concentration and rate. Now, and that's what we're saying, that the rate is at the highest at the beginning of the reaction and will gradually decreases and become slower and slower with increase in time. Now, when you're now talking about the rate of reaction, we're talking about the mathematical representation, because something is very, very important that we said originally, that the rate is not constant. You need to keep that at the back of your mind. The rate of reaction is not constant throughout the reaction. It changes. And the reason why it changes is simply because the concentration is also changing. And rate depends on concentration. Now, the formula for determining the rate of a reaction, or the rate equation, or this is actually called the rate equation. This is not the formula. I won't call this the formula for determination of rate of reaction, but we call this the rate equation, or the differential rate equation. So if you want to use A to determine, from the curve we showed earlier, if you want to use the concentration of A to determine the rate of reaction, then what you're going to do is you want to look at the difference in A divided by the difference in time. The original concentration, or sorry, minus the final concentration divided by the original time minus the final time. We'll do that in detail. Then there's another factor that also contributes, that is the catalyst. We have the effect of catalyst. Because remember, we already spoke about the nature of the reactant, pressure, concentration, temperature, and now we are talking about catalyst. Now, the price of a catalyst can increase or decrease because there are catalysts that are actually used to slow down the rate of reaction. They are used to inhibit the rate of reaction. So the presence of a catalyst can increase or decrease the rate of a particular reaction. So, for example, if you're reacting hydrogen and oxygen, or they don't just combine. They don't just combine without a catalyst. This is you can't just have hydrogen and oxygen and you expect a reaction. No. But when you have a platinum catalyst present, you're going to have a rapid combination to form water between H2 and O2, between hydrogen gas and oxygen gas in the presence of a platinum. Now, that means that what you're having is that a catalyst is speeding up that reaction. It's speeding up the reaction. And the reverse is the case when you're talking about the composition of hydrogen peroxide. If you add a small amount of glycerin or acetanilide into hydrogen peroxide, this slows down the decomposition of hydrogen peroxide. That's why if you call it a catalyst, it does not necessarily mean that it increases the rate every time. Some increases the rate. It's all about change of rate, really. It can increase the rate. In certain situations, you reduce the rate. So that is the last factor and how it affects rate of reaction. Now, how do we now determine reaction rate? We already spoke about chemical kinetics, the relationship with rate of reaction. What does rate of reaction mean? What are those factors that affect rate of reaction? But mathematically now, how do we even determine rate of reaction? Because essentially that's the first thing we're going to be learning, or is the first important thing that we really need to learn, apart from the introduction that we went through. Now, rate of a reaction is actually it's comparable to the speed of a car. Rate of reaction is comparable to the speed of a car. Remember, if you want to determine the speed of a car, you will look at the distance traveled and you will look at the time used to cover that distance, or the time it took to cover that distance. If a car covered 1,000 kilometers in 20 hours, you already know that the speed of that car is going to be 1,000 kilometers divided by 20 hours. That will be the speed. It is the same thing with rate of reaction. The rate of reaction, the distance is the concentration in the rate of reaction. The time is still the same. While you're considering distance for speed, you're considering concentration for rate of reaction. Now, if you start a reaction, say you have reactant A, just like we showed earlier, reactant A plus B, and that reactant A, you're starting with 5 mole per dm cube of reactant A. And after 20 minutes, you check the concentration of that reactant A. Now you have 15 mole per dm cube. Now you know that you already consumed 5 mole per dm cube in the course of the reaction. And the fact that you already consumed 5 mole per dm cube in the course of the reaction, then you already spent, say it took you 5 minutes, you're checking at the end of 5 minutes. Then that means you're going to be doing 20 minus 15 divided by the 5 minutes that it took you. That is why I said rate of reaction is comparable to speed. The distance is comparable to concentration, while time remains the same for both, really. So the rate of a chemical reaction is similarly defined as the change in concentration of a reactant in a particular interval. Change in concentration of a reactant in a particular interval. You're starting with 20 mole per dm cube. At the end of 5 minutes, now you have 15 mole per dm cube. You know you already have a change of 5 mole per dm cube in 5 minutes. Now you know that the rate of reaction is going to be 5 divided by 5, which is going to be 1 mole per dm cube per minute, really. But we're still going to look at examples anyway. But I'm just using that to explain what you have on the slide. Since concentration is normally measured in mole per liter or mole per dm cube, the rate of reaction is specified with a unit, because if the calculation is concentration divided, or change in concentration divided by change in time, then it means that the unit is also going to be the unit of concentration divided by the unit of time. The unit of concentration is mole per liter or mole per dm cube, which is what you see here, divided by the unit of time, which is the SI unit here is second. So what you're going to have is going to be mole per liter per second. Now, let's now look at an example. So for example, consider this specific reaction where you have a decomposition of gaseous nitrogen pentoxide. So you have that decomposition to give you nitrogen 4 oxide and oxygen. Now, you can determine the rate of this reaction by measuring the increase in the molar concentration, because you can, like I said, you can use any of this, any of this 3 to determine the rate of reaction. Now, but at the end of the day, something is also very, very important. You can see that the number of moles of these reactants and concentrations are different, and they need to be taken into consideration. Because you have 2 mole of N2O5 to give you 4 mole of NO2 plus 1 mole of oxygen. Before we begin to talk about the mathematics, I think we just need to understand how these 2, 4, and 1, how it affects the rate. Now, what this is saying is that you need 2 mole of nitrogen pentoxide to produce 1 mole of oxygen. 2 mole of nitrogen pentoxide to produce 1 mole of oxygen. Now, what this is saying is that you consume 2 mole to produce 1 mole. It means that the rate of consumption of nitrogen pentoxide is higher than the rate at which oxygen is being produced. I'll repeat that again, because this is very, very important to you using this to do your calculation. 2 mole of nitrogen pentoxide will give you 1 mole of oxygen. What this is telling you is that the rate at which you're producing nitrogen pentoxide is faster. Sorry, at which you're consuming nitrogen pentoxide is faster than the rate at which you're producing oxygen. Now, if you also compare N2O5 with NO4, what that is telling you is that the rate at which you're consuming N2O5 is slower than the rate at which you're producing NO2. Because if you're consuming 2 mole of this just to produce 4 mole of this, now it means that the rate of consumption of this is lower than the rate of production of this, because you're producing more of this, 4 mole, while you're consuming 2 mole of this for every consumption of 2 mole. You can even compare these 2 reactants. For O2, it means that the rate at which you're producing NO2 is faster than the rate at which you're producing O2. Now, the question is, which rate are you going to be using? Because we're saying that, oh, this rate, which rate are you going to be using? Which you need to pay attention to, because we're going to be talking about those relationships. But know that if you're looking at the rate of this, looking at the rate of this, looking at the rate of this, you're going to end up with different values. If all you're doing is, oh, I just want to monitor the rate, the concentration of NO2, you will have a rate from that. I just want to monitor the concentration of this, you'll have a rate from that. I just want to monitor the concentration of it, you'll also have a rate from that. But at the end of the day, which one is actually going to be your rate? Or how do you determine your rate from all those three? Now, but before we get to that, let's just look at oxygen, since oxygen is just the one with the 1 mole here, because it's just a mole, because it's going to be our gold standard. Is the one with the lowest number of mole, that's going to be the gold standard. So what do? You look at the final, since it's a product, you're subtracting the original concentration from the final concentration. And let's look at that again, because you want to determine the change in concentration of your species by the change in time. So the change in concentration is going to be the original concentration of oxygen, the final concentration of oxygen minus the original concentration. That is the final concentration minus the initial concentration. So that will be the change in concentration of oxygen divided by the change in time. So that's what you have here. Rate of formation of O2. That is what you have here. And remember that I said you can determine the rate from, you can determine one rate here, one rate here, one rate here. So for oxygen, the final concentration minus the initial concentration divided by time. Is the same thing also for nitrogen pentoxide, which is the... Now, this is important. I need to mention this. You can see that there's a negative here, there's no negative here. I forgot to mention that, I'm sorry, because we're supposed to also talk about that. You have a negative, because when you're writing rate of formation of O2, there's no negative there. But when we're writing the rate of decomposition, there's a negative. Now, the reason for that is simply because the rate of formation of O2, in the rate of formation, or when you're using a product to determine your rate of reaction, concentration is increasing. Concentration is increasing. So when you do your final minus initial, like we did here, you're going to get a positive value because it's a product. If you look at this reaction, at the beginning of the reaction, we won't even have any oxygen at all. Meaning that original concentration is going to be 0. And at the end of the reaction, we are going to have some concentration for oxygen. Meaning that we're going to be subtracting 0, which is the initial, from that final concentration. That means the value is going to be positive. But if you're using this, remember, the concentration decreases with time. Your initial concentration is going to be higher than your final concentration, and that change in concentration is going to be negative. And that is why when you write this, as long as it's a reactant, you're going to have it. When you're writing rate of rate of consumption of a reactant, there has to be a negative. When you're writing for a product, you don't need a negative because it's positive. And that is the reason why one is negative and the other one is positive. So we already spoke about the unit. Of course, there are varieties of units, and I already told you how we arrive at the unit. Since the concentration is concentration divided by time, then it means that the unit is also going to be the unit of concentration divided by the unit of time. So mole per liter, that's the concentration of the concentration. Second is the concentration of, mole per liter is the unit of concentration, while second is the unit of time. And that is why the unit is mole per liter per second. And if you want to use per minute, you still have it. You want to use per hour, say if your time is in second, is in minutes, is in hour, then you have it. Now, we're now what I was talking about, the relationship between concentration of reactants and product. Now, if you look at this reaction, for the equation, 2 moles of N2O5 are required to produce 1 mole of O2. I think I already explained this. But now it means that if you now, because you should be able to put an equality sign between any two of this. You should be able to put an equality sign. What you're going to get here, if you're monitoring just the reactant, you're going to have a rate. But that rate is not going to be the same thing as if you're monitoring the rate of NO2, because the number of moles are different. The number of moles are different. And at the end of the day, we said you can monitor any one, or you can use any one of this. But the most important thing is that your gold standard is going to be the one with the 1 mole. Now, are required to produce 1 mole. So in other words, the rate of decomposition of N2O5 is twice as fast as the rate of formation of O2. So if you now want to equate the rate of formation of O2 to rate of decomposition of nitrogen pentoxide, this is what you're going to have, because if the decomposition of N2O5 is twice as fast as production of O2, it means if you want to equate both to each other, you're going to have to either divide this by 2, or you're multiplying this by 2. But of course, we can't be multiplying anyway because we need the exact rate. So, and of course, this is the one that is actually the lowest. And you're dividing this by 2 because 2 of nitrogen pentoxide is producing 1 of oxygen. And if you're comparing nitrogen pentoxide, you're comparing nitrogen 4 oxide and O2, this is what you have, because the rate of formation of NO2 is 4 times as fast as the rate of production of O2. So if you want to equate both to each other, you're going to have to divide this O2 by 4. Because what you need is the rate of formation of O2. So if you need the rate of formation of O2, and you want to find the rate of formation of O2 from NO2, from the rate of formation of NO2, then that means you're going to have to divide whatever you have for NO2 by 4. I'll take that again because I don't want any confusion around this, because these are important questions that you are likely going to be getting. You're definitely going to be seeing as you go through this course. You have 4 NO2, 2 N2O5 to give you 4 NO2 plus 1 molecule of O2. You want to determine the rate of formation of O2. If you want to determine the rate of formation of O2, you can use any of this. You can use N2O5, you can use NO2. But you need to look at the mole relationship, the mole ratio between oxygen and any of the one you're using. If you're using NO2O5 and you want to determine the rate of formation of oxygen from the rate of consumption of N2O5, you can see that 2 mole of N2O5 is consumed to produce 1 mole of oxygen. It means the rate at which N2O5 is consumed is faster, or is twice faster than the rate at which O2 is produced. And you need the rate of formation of O2. So that means what you do is, just like we did here, what you do is you determine the rate of formation of, the rate of decomposition of N2O5 first. When you have that, you know that that is not the rate of formation of O2, because that one is faster than the rate of formation of O2. By how much? It is faster by double, really. Then that means you need to divide it by 2 to get the rate of formation of O2. If you're looking at N2, if you want to determine from the rate of formation of NO2, then you'll also look at the mole ratio also. It is 4:1. It means that the rate at which NO2 is being produced is faster by multiple of 4, the rate at which O2 is being produced. That means you determine the rate at which NO2 is produced. When you have that, you know that that is not the rate at which oxygen is being produced, because it is 4 times faster than the rate at which oxygen is being produced. Therefore, you need to divide that by 4 to give you the rate of production of oxygen. And that's why you have the rate of production of oxygen is equal to the rate of production of NO2 divided by 4. Now, the relationship between concentration of reactants and products. We are still going to run, what we have is explanation. We still have examples where we're going to have like complete examples to those analogy, really. But I just want the analogy to be clear. So don't think we've ended our examples there. No, we've not ended the examples. Now, this is just an example of what you do when you're looking at the rate of reaction. There's something called average rate of reaction. There's something also called instantaneous rate of reaction. What we have been talking about till date has been average rate of reaction. That is, you're just looking at a particular time interval. And remember, we call it average rate because even at every point along that reaction, the rate keeps changing. As the concentration changes, the rate changes. But the only thing you just need, you can't be, since you don't need, you just want to have an idea what was the rate across that time period. Oh, after 1 hour, what was the rate of reaction? So what you're calculating will be average rate. Because if you're calculating the rate after 1 hour, the rate after 10 minutes is not going to be the same thing as the rate after 20 minutes. It's not going to be the same thing as the rate after 30 minutes. That one also won't be the same thing as the rate after 40 minutes. But if you're calculating the rate after 1 hour, you're calculating an average of all those different rate of reaction. And that's why it's called an average rate of reaction. Why the instantaneous rate? Is the rate at a point, really? You can say, okay, at 10 minutes, what is the rate? We'll talk about how to do that, where you draw a tangent. But again, look at this. This is the time. We're having the reaction we mentioned earlier, N2O5. At 0 second, at 184 second, at 319 second, at 529 seconds, at 3865 seconds. And this is the change in concentration. Concentration is changing from here. At zeros, you started at 0 time. You started at 2.33 mole per liter. But after 184 seconds, the concentration has reduced to 2.07. Then after 3.19 seconds, the concentration has also reduced to 1.91 mole per liter. After 529 seconds, the concentration has also reduced to 1.68 mole per liter. After 867 seconds, the concentration has also reduced to 1.35 mole per liter. Now, what is the rate when you move from 0 time to 184 seconds? That is after 184 seconds, what is the rate of reaction? Now, what that means is that you are going to be subtracting 2.07 . So what you're going to be doing is you subtract 2.07 from 2.33. Well, the right thing is final minus initial anyway, so that you can actually see the negative. So it's going to be 2.07 minus 2.33 because it's final minus initial divided by 184 seconds. Because your time is going to be 184 minus 0, so that this is what you have. But we have an example where that is dealt with. This is the example. In terms of the reactant N2O5, we use this equation. This is the equation. That is the final concentration of N2O5 minus the original concentration of N2O5. Now, in this case, the calculation that was done was to find the average rate between 319 seconds and 529 seconds. That is from here, 319 seconds. So you want to see the rate, not the rate from the beginning to this place. You can do that also. But that example is only dealing with the rate from 319 to 529. That what is the rate between here and here? Now, if you want to calculate between 319 seconds and 529 seconds, this is the concentration at 319 seconds, and this is the concentration at 529 seconds. So now that means we're subtracting 1.68, which is concentration at 529. Oh, sorry, we're subtracting the concentration at 319 because that is 1.91. So the concentration at 319, which is 1.91, from the concentration at 529, which is 1.68. And that is what you have as the numerator. Then for change in time, remember, we're dealing with 529 and 319. So you're subtracting 319 from 529. And the answer to that is 1.11 times 10 raised to the power minus 3. That is the rate of reaction, the average rate now. between 319 to 529. If you're to do from average rate from the beginning to 529, then it means you're going to be subtracting 2.33 from 1.68. And your time is going to be 0. It's going to be 529 minus 0. So it's just the same thing. You follow the same procedure. But again, like I said, we have what is called instantaneous rate of reaction, which is but I decided to just mention it. Is the rate at any specific time. When you say instantaneous, at an instant, because that is what instantaneous means. At a particular instant, at a particular time, what is the rate of reaction? So the rate of reaction at an instant is, because remember, this is average. We're saying from a particular time to a particular time. At an instant, it's going to tell you a particular time. At this particular time, it can be at 184 seconds. What is the rate of reaction at 184 seconds? What do you do there? You just draw a tangent. We'll explain how to draw that tangent when we get to how to determine order of reaction. But the formula is still the same. You're still going to be subtracting the original, but those ones are much more imaginary. They're not the kind of value you generated yourself. You're going to be looking for them on your chart. Now look at this. How might the rate of reaction of the following equation be expressed? You have this, and you want to see the rate of the rate of this reaction. In this case, you're having H2 reacting with I2 to give you 2 mole of hydrogen iodide. So if you want to talk about the rate of reaction is just going to be either the rate of consumption of H2 or the rate of consumption of I2, or the rate of consumption of hydrogen or the rate of consumption of iodine. So, and remember, both are 1-1. So you can use any of the two to determine the rate. But I'm sorry, there's something on this slide that has disappeared, because we also did using the 2HI. Or is this still somewhere here? I think it has disappeared. I think it was written here. So I'm sorry about that, but I think I'll just explain what is there, because this is too straightforward, and that's why we had the second one. Because this one is 1:1. So of course, we don't have the rate at which hydrogen is consumed is the same thing as to which iodine is consumed. So they are equal to each other. And of course, pay attention to the negative also. But if you want to bring hydrogen iodide into the mix, if you want to bring hydrogen iodide into this mix, you can see that the rate at which hydrogen iodide is produced is twice as faster as the rate at which either hydrogen or iodine is consumed. Meaning that if you want to bring this in, this is going to be is equal to delta hydrogen iodide divided by delta T divided by 2. Because you're going to have to divide this by 2. It is important, because the rate at which it is produced will be faster than the rate at which hydrogen and iodine is consumed. So if you want to use iodine to determine, if you want to use hydrogen iodide to determine the rate at which either hydrogen or iodine was consumed, then you're going to have to divide that by 2, because its rate of formation is twice as fast as the rate of consumption of hydrogen iodide. And that's why anytime you want to determine rate of reaction, you must pay attention to those mole, especially when you're having this kind of question. You must pay attention to those mole ratio. Now let's look at a conspicuous, or shall I say a much more detailed example. At some time, it was observed that in the reaction we've been using, the rate of formation of NO2 was 0.0072 mole per liter per second. What is the rate of change of O2? That is delta O2 divided by delta T in mole per liter at that time. Sorry about that. They just brought light and that was on. So the rate of formation of NO2 was 0.0072 mole per liter per second. So now they're telling us that the rate of formation of NO2 at a particular time was 0.0072 mole per liter per second. Now, at that particular time, now they want to know the rate of change of O2. That is the rate of formation of O2 at that particular point in time. And now, we need to look at the mole ratio. You can't answer that question without paying attention to the mole ratio. It's very important. Now, the second question is, what is the rate of change of N2O5? You can't answer that question also without paying attention to the mole ratio. What is the rate of reaction at this time? Now, let's look at how we answer those questions. Now, number one, because to answer this, you know what is the relationship between oxygen, the rate of formation of oxygen, and the rate of formation of NO2. It is 1:1. So 1 mole of O2 will give you 4 mole of NO2. That's the first thing that you need to know, because that's important. And if you've been told the rate of formation of 0.007, the rate of formation of NO2 to be 0.0072. Now, and if the ratio is 1:4, you already know that you're only going to divide this by 4, because we already know the ratio that we already know the what is it called? The ratio of their rate. It is 1:2. Sorry, it is 1:4, and that's why now your rate of change of O2 will be 0.0072 multiplied by that mole ratio, which is 1 divided, because the mole ratio is the same thing as the ratio of their rate. The mole ratio is the same thing as the ratio of their rate, because remember, when we're talking about the ratio of their rate, we're looking at the mole ratio, nothing else. Nothing else. We're looking at the rate, we're saying, okay, this is 1:1, and we're saying, okay, the rate at which this is produced is 4 times as fast as O2. We're only looking at mole ratio. And that's why what we're using here is just mole ratio. So if you now use the mole ratio, 0.0072, multiply by that mole ratio, which is 1 divided by 4, that will give you 0.0018 mole per liter per second. The second part of the question takes the same form. It takes the same form, N2O5. Now, if you look at this again, it is 2:1. It is 2:1 or 1:2 now. Oh, sorry. Okay, sorry, what am I saying? Okay, sorry. Oh, it's 2:4, sorry. Because remember, we're comparing NO2 because we're not given oxygen. We can use oxygen also to do that calculation anyway. It's not that we can't, but we want to keep this very straightforward. So we're giving oxygen, so we're giving NO2. So it's the comparison between NO2 and N2O5 now. So this is going to be 2:4 because this is 2, this is 4. Now, that means we have 2:4, but we are putting negative now because NO2 is N2O5 is a reactant. That's why you see the negative there. N2O5 is a reactant. While N2O5 is decreasing, NO2 is increasing. That's why you can see we have the negative. So eventually, our answer or our calculation will now be the rate of formation of NO2 multiplied by that mole ratio, which is -2:4. And you have 0.0072 multiplied by -2 divided by 4. The reason why you're having that negative is so that at the end of the day, it will show that it's a reactant. Because if it's a reactant, the negative is telling you that the concentration is decreasing. The negative is telling you that the concentration is decreasing, not increasing. For oxygen, there is no negative because the concentration is increasing. Now, how do we now? Remember, there are 3 questions here. The first one is to calculate the rate of change of O2 using the rate of change of NO2. The second one is to calculate the rate of change of N2O5 using the rate of change of NO2. Why the last one is to calculate what is the rate of this reaction itself, because there are 3 rates of reaction here now. So which one is the rate of reaction? Because like I said, you can use any of this, but at the end of the day, you must build it down to 1 mole. If you're using N2O5, remember, where is it? If you're using N2O5, it's going to be 1 mole. Sorry, whatever you have here, you divide it by 2. If you're using NO2, you divide by 2. If you're using NO2, sorry, if you're using O2, that's just 1 mole. You don't need any division. Whichever one already has a mole ratio in front of it, apart from 1, you try to divide. You try to divide that one. So since NO2, we have 0.007 for NO2. If you want to use NO2 to determine the rate of reaction now, you're going to divide that by 4. You're going to divide that by 4. We already did for because at the end of the day, we must get the same thing. It doesn't matter what you're using. If you're using O2, we must get the same thing as NO2. We must get the same thing as N2O5. So it doesn't matter what you're using. We must get the same because the rate because it's the same reaction. The rate has to be the same. So if you divide this by 4, you will get 0.0018. And O2, you are not dividing by anything because it's just 1 mole. It's the lowest there. So the rate is still going to be the same thing that we had here, which is 0.0018. So you see now, you're using N2O5 because it is 2 mole, you're dividing by 2. You get 0.0018. When you're using NO2, you're dividing by 4. You get 0.0018. So determining the rate of reaction, you can use any of the reactants. All you need to do is pay attention to the mole ratio. Now, so that is how to determine the rate of reaction from your reaction data and your rate and your chemical equation, paying attention or while taking cognizance of the mole ratio. But there is something called, when we started this course, I think I'll just take you back to it so that you know that we're not just jumping to it, because I said that we're coming back to talk about it. The rate law. This is it. You know, where I showed you this, I said, okay, this is the rate law. That I'll still talk more about what it means, really, and how, what does it mean? How do we use it? So, and that's what we want to talk about next now. Oh, okay. Has my time ended? Coordinator.
You have another course now.
Oh, okay.
Thank you, sir.
All right. So I'll see you next class. Thank you very much. Somebody raising hand here.
Me has a question, sir.
Yes. Okay. Can you mute him? Olayemi, your question.
Unmute yourself.
Unmute yourself.
I'm unmuted myself. Good morning, sir.
Good morning.
Okay, sir. The first part where you gave the equation, the reaction 2N2O5 in gaseous form to give 4N2O2 plus O2 in gaseous form O2. I said, yes. I said the first, there are 2 moles of N2O2 react to produce 4 moles of NO2 and O2 gas, but you use O2 as this thing. The composition, the rate of the composition. Is it that is this thing? The reaction that has the smallest mole number that we always use for the rate of reaction.
Because at the end of that's your gold standard. The one with the lowest is actually the one that you get to use eventually.
Okay, sir. The second question is if you are calculating for the rate of reaction for this thing for a reactant, that means the equation will be negative.
if you're using the reactant, concentration of the reactant, you will end up with a negative value because you're subtracting initial from final. And you know that the initial for reactant will be higher than the final.
Yes.
Is that clear now?
Okay, sir. Thank you, sir.
All right.
Yes,
Any other question, please? Any other question? Okay, somebody, okay. Ashade Temilayo. Ashade Temilayo. Coordinator.
Are you willing to take Temilayo's questions, sir?
Yeah, yes, I'm here. Let me take
so
it.
Unmute yourself, Temilayo. Unmute yourself. I think it's not.
Okay.
Can you explain positive and negatives? Maybe you can answer all that next time.
Okay, let's do this. The first 5 minutes, in next class, the first 5 minutes, I will use it to quickly attempt to 1 or 2 questions before we commence the class next time. So anybody with a question, we'll just take 1 or 2 questions at the beginning of the class, because I will also want other students to benefit from the response to the questions.
When can we have the slides?
Yes, coordinator, that's for you to decide.
Send to me as long as once you are sure you are ready to send to them.
Okay, all right.
PDF version.
PDF, yes, I'll send it to you now.
Thank you, sir.
All right. Good morning.